Okay, physical science time. Today we are talking about science, the SI, and conversions. That's a very important. I'm actually, instead of writing conversions, I'm not going to erase it. I'm going to put a line through and put dimensional analysis. So if you could please write down the heading and the objective. Today's objective, as you can see from the board, is describe science and the measurements used in science fields. Describe, so please write this down too, describe science, I'm going to put that in all caps, and the measurements used in science fields. It's a field. Yeah. She needs wide open places. That's what a field is. No, what do you probably know. When we're talking about fields of a subject, what does that mean? The different areas, kind of a similar feeling, a similar vibe to the word fields, like a wide open space, but you're right, an area. It's obviously some kind of metaphor, right? So it's a what? You may put your phone on silent. Thank you for asking. How about this? Give me an example of a field in science. What's one of the fields of science? Chemistry. Physical science includes both physics and chemistry, but chemistry is one, physics is one. What's another field within science? We might say, you said areas. What kind of areas are they? Areas of the science. Subject areas. They are subject areas within science. Chemistry, physics. What's another one? There are really two more main ones. Plant. It's broader than that. All kinds of life. What do we call the science of all kinds of life? Biology. Yep. Okay. And then what's the other one that has to do with geology? And then with that, astronomy you might consider to be separate wholly, but usually, at least for the sake of degrees, Earth science is within space science, and so astronomy is usually considered a part of Earth science, which is kind of like the opposite. But anyway, so those are the fields of science. And science in general, science comes from the Greek word, no, probably the Latin word, it is Latin, scientia, which means to know. But it's not the things we know, strictly speaking. It's not. A lot of times, especially when we come from elementary science, we're used to thinking of science. Science is things like plants, the planets, the human body. Those are the subjects within science, and it's true, those are the things we often are talking about. But science is really a way to know. It's a process of knowing, which we call the something method. Do you remember? The scientific method. How many steps are there in the scientific method? Well, it's a trick question. There may be, your book gives 6 and then a branch where there's 2 of them, and so really there's like 8 different steps, but you only use 7 of them. But I would say generally and basically, we can boil the scientific method down to 3 broad steps. There's some kind of problem, there's some kind of investigation, and there's some kind of conclusion. So your book says that the steps are state the problem, gather information, form a hypothesis, test the hypothesis, analyze data, draw a conclusion, and then depending on whether or not the hypothesis is supported, we go back and modify or accept the hypothesis. But a lot of those things are within investigation, right? So maybe like the testing the hypothesis and analyzing the data are within the investigation here. And then the conclusion, we'll draw a conclusion. What if we want to report our findings? Well, that would be within the conclusion, wouldn't it? Let me give you an example. The kind of two-pronged example we use in something like a hard science, like maybe we're doing research about what kind of butterflies there are in Dawes County. What kind of butterflies there are here? Well, we have a problem, but our investigation can't just be go into Google and type in what kind of butterflies are there. Because that's the research we're doing. We're trying to figure that out. And so we're going to, maybe our investigation encompasses going out and collecting a load of butterflies and enumerating them all. And then for a conclusion, we write a scientific paper about that. And there's a lot more steps within each of those. But it can be as simple as Cameron's watching Transformers and like, oh, who's that cute girl? That's the problem. And the investigation is you type in Google, who's the cute girl in Transformers? And the conclusion is, I don't know your life. Maybe it's someone else. Maybe it's some other girl. I'm positing to you that even some little simple problem in your life like that, maybe that's a big problem for you, I don't know, but some little problem for you in your life, you are actually using the scientific method to solve. In a way, you're not doing the kind of strict science that we're talking about when we're doing an investigation of butterflies, but you are using the scientific method to solve a problem. It's all about problem, oh, this is a nice marker, problem solving. The way we solve problems, the way we know about the world is science. When we're doing hard science, or when we're doing science that it uses the more of the steps of what we normally think of as a scientific method, our investigation might include variables. Do you remember our discussion of variables? You have one of your worksheets is SpongeBob SquarePants variable thing. What kind of variables do we talk about in science? Do you remember? Independent, dependent, and then we have sometimes a control group, and then we have constants. What's the independent variable? You should write no, that's not right. You should write the definitions for these down. I don't really have them, so I'm just going to leave them, but we'll talk about them. Let's start from the bottom, actually. What are some constants in an experiment? What does that word constant mean? Yeah, that means it doesn't change. They're the things that we choose not to change about the experiment. You'll remember from algebra that you can really only reasonably solve an equation, at least in algebra, with one variable, right? If you end up with two variables, well, depending on what those two variables are, they might change with each other, and you can solve for the change between them, but you can really only solve for one variable algebraically. And so everything else needs to stay the same, and that's true in science too. We need to keep everything else the same. If I'm trying to think of an example from your lives that you might want to change. Maybe you're trying to get rich, and so you try a lot of different things to get rich. So you put your money in lots of different accounts, and you don't actually know which one's working because you've changed so much stuff. A better way to do it would be to change one thing at a time. So the things that we keep the same are the constants. In an experiment like, if we're seeing what kind of milk curdles the fastest, we have whole milk and skim milk and 1% and 2% and oat milk, and which one curdles the fastest, which one goes bad the fastest. Our constant might be, well, we can't like put the 1% in the fridge and the 2% in the freezer and put the oat milk on the front porch because we're changing too much stuff, right? We've got a difference in the kinds of milk, but we're also changing their environment. So we would want to keep that the same. We keep them all in the same place. What might a control group be for that? Well, we might have a little cup of water or something to make sure that something about our environment is not itself destroying the milk. So the control group is something kind of separate from the experiment that we don't change anything about it. And then we have these two variables left, the independent and the dependent. What's the real difference between those two? You remember?
The one like changes the other one.
Okay, yeah, the independent variable is usually something that we ourselves, as the experimenter, change. We're introducing that variable. The dependent is the variable that there's a nice verb that kind of is really actually almost like a cheat code that you can use to tell which one is which, is that you can ask, what do we do with the dependent variable? We measure it. Whatever thing we're measuring is the dependent variable. So in that experiment, what would the dependent variable be? A lot of times it's easier to start with that one. In the experiment of the milk, what would the dependent variable be? The fastest, yeah, how much time it took to curdle. And then the independent variable is which one? The independent variable is the type of milk. Should we do another example, or do you think you got it? Let's do another example. Let's say you plant 3 fields of wheat And one of them you treat with weed killer of type A, one of them you treat with weed killer of type B, and the third one you don't treat at all. First of all, which one's the control group? The one that's untreated, the one you didn't treat with weed killer at all. What are some constants? What are some things that we leave the same? Yeah, hopefully the kind of plant, right? If we started messing with the kind of wheat it is and the weed killer, how would we know, based on the yield, whether it was the wheat kind or the weed killer? We wouldn't want to change a lot of other stuff. So the kind of wheat, the kind of dirt, someone said, what else? The amount of water, hopefully. I mean, a lot of times we don't irrigate wheat sometimes, and so maybe just the amount of water we're trusting will be the same because of the rain. What is the dependent variable? What are we measuring? Yeah, how much wheat we get, probably. The yield of the wheat. What's the independent variable then? Not Streety. What's the independent variable?
The variable that does not change.
No, that's not. We already said that's not it. That's a constant. What's the independent variable? I'm not looking for that definition. In my wheat experiment, what's the independent variable? Not how much, but the kind of wheat killer. We had type A and type B, so the kind of the wheat killer is the independent variable. A lot of times it's easier to kind of go up this list. I will say, specifically for your labs, a lot of times it's easier for you to figure out what the dependent variable is, and then you can tell what the independent variable is from that. What are you measuring is the dependent, and what has caused that difference is the independent. In science we use, I'm going to switch colors so I'm now switching topics. In science we use a measuring system that a lot of us are unfamiliar with called the SI, but hopefully you'll get more familiar with it. SI stands for, in French, the Système, I think it's those two little accents, International. And that, can you guess what this means in French?
International.
The international system, yeah. I tell you the French, not just to be highfalutin, although that is true, but because it's abbreviated SI. In English, we would call it the international system, and so the abbreviation SI stands for the international system. It's kind of like a new metric system. The metric system was invented in Napoleonic France, meaning like in the early 1800s, maybe the late 1700s, to find a more mathematical way to perform measurements that relied less on what people's opinions were. And so the metric system was invented then, and then it was kind of revised in later years to become the System International, or the international system. And there are 7 base units, 7 what we call base units. And the base units are what form the stable base. They form the base of the SI. Can you tell me what they might be? There's some of them I'm pretty sure you won't get, but not centimeters, because centi is a prefix, so that's not a base unit. But we're going to talk about that in a second here. But meter measures what? Length. Is foot on there? No, foot is not on there. The abbreviation for, I spelled length. I meant to spell length. There we go. And the abbreviation for the meter is M. Another one. What's another unit that we find in the SI? Liter is not one, because a liter is a cubic decimeter. Volume equals length times width times height, so that's a derived unit. So we have over here this idea of derived units, which are those that are modified, maybe we could say, modified from base units. For example, centimeter. Centimeter, meaning that it's 1/100th of a meter. That's what that prefix means, 1/100th. Or gram per milliliter. Gram per milliliter. These are units that are kind of scrunched together to make these derived units. Derived means comes from. Joe's name is derived from the Bible, the Joseph from the Bible. That's where it comes from. That's what derived means. Chocolate is derived from the cocoa bean. Derived means comes from. So these units come from other units. So what is another base unit? It's actually kilogram, even though I just said it has a prefix. But in this case, they pick kilogram as the base unit because it's more easy to use. I think it would make a lot more sense, especially for 9th graders, if it was just gram. But kilogram is the base unit for mass. I say there are 7 of them. What's another one? What's another basic thing we might want to measure? Mass, length, very common. We all use this one almost all the time. No, volume. Volume is a derivation of length. We use this all the time. I already gave you one. That's why I'm smirking like that. I can't help it. We use it all the time. Streety's looking at it right now. No. Time. Time. What do we use in the SI to measure time? What's the base unit of time?
Minutes.
No, seconds. Oh, sorry. Seconds measure time. Yeah, so milliseconds are a derived unit because they have a prefix. Minutes are a derived unit. Hours, etc. Weeks, months, days, all those are derived units. You might get another one, but then you probably won't get the rest of them, but it's okay. I'll tell you the rest of them. What's another one? What's a very common thing we measure in science that we haven't got up here yet? Very basic measurement. You could look about over there and find this one too. No. Door. Good. Close. Temperature. Temperature. We use kelvins to measure temperature. And then there are 3 more. The 3 more are electrical current, measured in amperes, which we talked about last year. Intensity of light, which is measured in candelas. And amount of substance. We'll talk about that one when you're in chemistry, and measured in moles. So there are these 4, those 3 that I just said, and those are the base units of the SI. And then all the other units that we use are derived from those in ways like adding a prefix or some kind of mathematical operation. The prefixes you need to know, let's make a little side note box here. The prefixes you need to know are centi. What's centi mean? 1/100th, and you should write these down. Milli, what's milli mean? 1/1000th. Kilo, which means 1,000 times. So 1,000 times more. And I think you should know that. Someone asked me about that on their chapter review yesterday. And those are the ones you need to know. Those are the prefixes that you need to know. There are obviously more, but these are the ones that you need to have memorized for this class. Usually in science we measure it in degrees Celsius, but degrees Celsius is a derivation of Kelvin. Degrees Celsius are the Kelvin temperature, which has no zeros. 0 on the Kelvin scale is absolute 0, plus 273.15 gives us Celsius. And so Celsius is a derivation of the Kelvin, even though Celsius came first, but Kelvin is the base unit. So Celsius is the derivation of Kelvin. Good question. And now the last thing that we have to talk about are, do you have questions about the Système International? You think hopefully you've heard all these words before, right? And you've heard these before. It's just these you need to memorize. You should be familiar with these. I think you are already, and you should know the idea of a derived unit. Now, I wish I could see whether or not this was a safe space to write, but I might erase my science discussion. Do you have questions about science itself before I erase it? The idea of variables or what is science? Anyone? Tristan, you good? Okay.
Oh wait, I mean.
Mason, ridiculous. Okay, now we're going to talk about what we sometimes call unit conversions. Unit conversions, or is more properly called dimensional analysis. And now this is a process. This, like science, is a process. I would love if you wrote down how to do these, because you're going to be tempted to do them wrong. There's a really easy way to get the answer to these things, but it's wrong. I don't want to see you do it, and there's 2 reasons. One, the very process of you doing this is going to expand your brain in ways that don't normally think about. It's going to be good for you to learn how to do this. And two, when you get good at them, it is actually faster and better and easier and will set you up for better things in chemistry and physics than if you just Google it. So we call them unit conversions because we're converting from one unit to another. The very, very easy example is, how tall are you, Zach? 5'5". Could we convert that to inches? Could we, yeah, of course. 5 feet is 60 inches. 5'5" would be 65 inches. Could we convert that to centimeters? Sure. Hey Siri, how many centimeters are in 65 inches? That's very easy. We could just do it like that, and then we can write down the answer. Or we can use, what's it called, photomath? We just do it, right? If we write 65 inches to centimeters and photomath it, it'll tell us, I'm going to try to think about it real hard for a second, 162 centimeters-ish, a little bit more. And then we're done. Now, okay, and that's fine for a person whose whole job is to wander around town and drink wine all day, just a wino. That's fine for them. That's fine for a citizen, a random citizen. But you all, that's plural, you are destined for better things, and you need to know how to do this process because, for one thing, as I said, it will expand your brain. Even if you never use this again, your brain will be expanded in ways that you will learn to do better problems. And if you take chemistry, which I hope you do, and you take physics, these become a much faster and better way to do a lot of different kinds of problems instead of having to think about it logically. The way we have this set up will be very useful to you. So let's do that exact one. Let's do it very briefly. This is how I want it to be. The first thing you do is you write down the given, 65 inches. This is called the, what did I just say? What's the word I just said? This is the given. Why would it be called that? It was, you were given it. It's the past participle of the word to give. Who gave it to you? Well, Zach, kind of, yeah. You were given the problem you were going to solve. So you first write the given with its unit. I tried to do like the voice of Mufasa because it's so frustrating to me. The whole point of this is that we're converting units, and sometimes people don't bother to put units with them. I'm going to make a little side break over here, and I'm going to put this with my side box. Every number should have a unit. Now, there are exceptions to that, but they're rare, depending on what kind of science you're doing. They're very rare. And I will tell you when that's true. Anytime we have a ratio, that's probably unitless, but that's about the only time. Every number should have a unit. I've said it before and I'll say it again. Units are nouns. That's what's telling us what kind of thing it is. 65 is an adjective. If I just say 65, that means nothing. I have to tell you what I'm talking about. Oh man, I had 65 last night. What? 65 what? 65 years of sleep? 65 dreams? 65 cats climbing around in my house? 65 root beers? You don't know, because 65 means nothing by itself. 65 inches? 65 inches is our unit, right? Inches is the unit. That's what we're talking about. The number is not anywhere near as important as the unit. So the first thing we do is write the given, including its unit. Then we draw this little fraction bar. We're going to multiply it by a fraction. So do that. Multiply by a fraction. Multiply by a fraction. What step are we on? Yeah, what number of step? Step 1, write the given. Step 2, we're going to multiply by a fraction. What do you think? What is this fraction going to equal? Are we changing how tall Zach is by doing this problem? Nope, we're just expressing it in different units. We're converting it to a different unit. What must this fraction be equal to then? What number? There's only one number in math we can multiply this by to make it so it doesn't actually change. 1. Multiply by a fraction equal to 1. That is so important. The fraction must be equal to 1. For this fraction to be equal to 1, what must be true of the numerator and the denominator? They're the same. They have to have the same value. They don't have to both be 1. They have to have the same value. So step 2 is multiply by a fraction equal to 1. Step 3 is let's put in our units. What unit are we trying to get rid of? What's the unit we no longer want to be using? Inches. So I'm going to put that. Look, there's no fraction here that we can see, but you know that inches is in what part of the fraction? If we can't see the fraction, inches is in the, try again, numerator. We put it on the opposite side of where it goes, so we put inches on the bottom. It's in the top here, so we put it on the bottom to get rid of it. I will use the phrase get rid of. Mr. Snilly does not like when we say things like reduce out and get rid of, but I think it's kind of useful, so don't tell him that. He won't watch this video anyway. So to get rid of the inches, we're going to put it on the opposite side of the fraction bar. So that's step 3. I'm going to put, for the sake of Mr. Snilly, in writing, I'm going to put reduce. This marker needs to go. G-O. Reduce to 1 by putting the unit on opposite side. I'll just put on opposite side. So it was in the numerator, we put it in the denominator. Now what unit do we want to go to? We said we were converting this from inches to centimeters. So I put the unit I want to go to on the same side as the one that the original was in. Now this fraction has to be equal to 1, doesn't it? So I need to find the numbers that are equal. How many, 1 inch is equal to how many centimeters? Does anyone know? Your test will tell you. Google will tell you. Eventually you'll have it memorized. If you have a composition notebook like I see Tristan has, open it up to the back and tell me 1 inch is equal to how many centimeters? No, you're in your backpack, the black one there. The very back of it will say, yep, open it up. The very back of it will say 1 inch is equal to
2.54.
There we go. But Mr. Keim, those numbers are equal and we're dividing. Well, they're equal because this fraction has to be equal to 1. We're not changing this value. We're multiplying it to just change the unit. So now all we do, step whatever I'm on, 4, good work. Step 4 is multiply by the, what part of the fraction do I multiply by, do you reckon? Numerator. Good. Divide by the denominator. So I take the given and I multiply it by the numerator and divide it by the denominator. What's 65 times 2.54? Oof, oof. There's a tool for you. There's a tool for you. You can use a calculator on these. Could you do this by hand? Sure. 65 times 2.54, you can do that by hand. This is not 3rd grade math. I trust that you could do that. Get a calculator and type it in right now. 65 times 2.54. Let the record show I said about 135, I think is what I said, but we'll see. 65 by 2.54. The point on that one is stuck with jelly or something.
I can tell.
What's the answer?
Can't tell this.
Can't do point. Okay. Get a different calculator that does have a decimal button that is functional.
Oh, yeah, this one works.
And he's typing in, tell us the digits you're typing in, Mason.
65.
No, that's not digits. 65
65 divided by
times
2.54. 165.
Oh, 165. I said something like that, right? Just now I said 135, but you can rewind the video. I think I said 160 something earlier. Anyway, 165. Oh, but we didn't divide by the denominator. What's 165 divided by 1?
165.
It's still 165. Now, we've done the math with the numbers, but now we do the math with the units. An inch over an inch, those things, don't say it. Don't say the bad word. Inch over inch, just like x over x, those, say it. Just say it. What's this? It's the same thing as these things do what? What do we say? What's the bad word? They cancel out. Yeah. So inches divided by inches cancel out. Ooh, that's a bad word. What are we left with? What unit are we left with? Centimeters. The answer is 165 centimeters. Now, you'll say, that took so long, I could have just asked Siri and she would just tell me. Sure, it took so long when you have to tell a group of bumbling freshmen how to do it, but it really is fast when you actually get to do it. So this is the correct way to set these up. Tomorrow, we will get more in depth about how to set up a little bit more, I guess, interesting, a little bit more complicated ones. They're not hard, they're just complicated. But for now, any of them on your worksheet that are just from one unit to another unit without any miles per hour or anything like that, you can do now. Just make sure you set them up like this, Tristan. Make sure you set them up like this and don't just write the answer. This is how I grade these. This is the last thing before we go. I guess you guys are going to leave 7 minutes early, so whatever. But this is how I grade these. 1 point, did you write the given? 2 points, did you write the correct conversion factor, this fraction? 3 points, did you put the units in? 4 points, do you have the right conversion factor within here? And 5 points, the answer. The answer itself is worth almost nothing. You're not going to get points on your worksheet if you do. Well, I mean, you'll get 1/5 of the points on your worksheet if you just have the answer. It's so much more important that you learn the process of this. If you did the whole thing right, but every single piece of math was wrong, or even you just didn't have an answer, that's an 80%. If you do the whole thing asking Siri and you have all the right answers, that's a 20%. Because I don't care about the answer. If I wanted to find how tall Zach was in centimeters, I too would look it up. But that's not the point. We're learning this process so that later you can do better things with it. Do you have questions about how to convert units? You can have questions about why we would convert units. I hope it's clear why we would do it. Now, your chapter review has 4 conversions. Number 28 on page 32, 1 through 30. Number 28 has A through D, and all of those are conversions. You need to set them up this way. You have a worksheet. You have a worksheet that is all conversions, and it has a back that is all conversions. Some of these are things like miles per hour or meters per second. That per we will deal with tomorrow, but any of them that are just simple conversions like seconds to days, you can do it like this. You can chain these together. If we, instead of going to centimeters, we're going to millimeters, we could just do one more conversion bar and go from centimeters to millimeters too.